This sound file contains the spoken word version of a Wikipedia article on the Oort cloud. It is recorded by user S_Whistler, and the material was recorded on the 2nd of April 2012. The Oort cloud, from Wikipedia, the free encyclopedia at en.wikipedia.org. The Oort cloud, or the opaque Oort cloud, is a hypothesized spherical cloud of comets which may lie roughly 5,000 astronomical units, or nearly a light-year, from the Sun. This places the cloud at nearly a quarter of the distance to the Proxima Centauri, the nearest star to the Sun. The Kuiper belt and the scattered disk, the other two reservoirs of the trans-Neptunian objects, are less than 1,000th of the Oort cloud's distance. The outer limit of the Oort cloud defines the cosmological boundary of the solar system and the region of the Sun's gravitational dominance. The Oort cloud is thought to comprise two separate regions, a spherical outer Oort cloud and the disk-shaped inner Oort cloud, or Hills cloud. Objects in the Oort cloud are largely composed of ices such as water, ammonia, and methane. Astronomers believe that the matter composing the Oort cloud formed closer to the Sun and was scattered far out into space by the gravitational effects of the planets early in the solar system's evolution. Although no confirmed direct observations of the Oort cloud have been made, astronomers believe that it is the source of all long-period and Halley-type comets entering the inner solar system, and many of the Centaurs and Jupiter family comets as well. The outer Oort cloud is only loosely bound to the solar system, and thus is easily affected by the gravitational pull of both passing stars and of the Milky Way galaxy itself. These forces occasionally dislodge comets from their orbits within the cloud and send them towards the inner solar system. Based on their orbits, most of the short-period comets may come from the scattered disk, but some still have originated from the Oort cloud. Although the Kuiper belt and the scattered disk have been observed and mapped, only 4 currently known trans-Neptunian objects, 90377 Sedna, 2000 CR, 2006 SQ, and 2008 KV, are considered possible members of the inner Oort cloud. Contents: hypothesis, structure and composition, origin, comets, tidal effects, star perturbations and stellar companion hypotheses, Oort cloud objects, modified Newtonian dynamics with the Oort cloud. Hypothesis. In 1932, Estonian astronomer Ernst Öpik postulated that long-period comets originated in an orbiting cloud at the outermost edge of the solar system. In 1950, the idea was independently reviewed by the Dutch astronomer Jan Heinrich Oort as a means to resolve a paradox. Over the course of the solar system's existence, the orbits of comets are unstable. Eventually, dynamics dictate that a comet must either collide with the Sun or a planet, or else be ejected from the solar system by planetary perturbations. Moreover, their volatile composition means that as they repeatedly approach the Sun, radiation gradually boils the volatiles off until the comet splits or develops an insulating crust that prevents further outgassing. Thus, reasoned Oort, a comet could not have formed while in its current orbit and must have had an outer reservoir for almost all of its existence. There are 2 main classes of comet: short-period comets, also called ecliptic comets, and long-period comets, also called nearly isotropic comets. Ecliptic comets have relatively small orbits below 10 AU and follow the ecliptic plane, the same plane in which the planets lie. Nearly all isotropic comets have very large orbits, on the order of thousands of astronomical units, and appear from every corner of the sky. Oort noted that there was a peak in numbers of nearly isotropic comets with aphelia, their farthest distance from the Sun, of roughly 20,000 AU, which suggested a reservoir at that distance with a spherical isotropic distribution. Those relatively rare comets with orbits of about 10,000 AU have probably gone through one or more orbits through the solar system and have had their orbits drawn inward by the gravity of the planets. Structure and composition. The Oort cloud is thought to occupy a vast space from somewhere between 2000 and 5000 AU to as far as 50,000 AU from the Sun. Some estimates place the outer edge of the Oort cloud between 100,000 and 200,000 AU, 1.58 and 3.16 light-years respectively. The region can be subdivided into spherical outer Oort cloud of 20,000 to 50,000 AU and a donut-shaped inner Oort cloud of 2,000 to 20,000 AU. The outer cloud is only weakly bound to the Sun and supplies the long period and possibly Halley-type comets to inside the orbit of Neptune. The inner Oort cloud is also known as the Hills cloud, named after G.J. Hills, who proposed its existence in 1981. Models predict that the inner cloud should have tens or hundreds of times as many cometary nuclei as the outer halo. It is seen as a possible source of new comets to resupply the relatively tenuous outer cloud, as the latter's number are gradually depleted. The Hills cloud explains the continued existence of the Oort cloud after billions of years. The outer Oort cloud is believed to contain several trillion individual objects larger than approximately 1 kilometer, with neighboring objects typically tens of millions of kilometers apart. Its total mass is not known with certainty, but assuming that Halley's comet is a suitable prototype for all comets within the outer Oort cloud, the estimated combined mass is 3 times 10 to the power of 25 kilograms, or roughly 5 times the mass of the Earth. Earlier it was thought to be more massive, up to 380 Earth masses, but improved knowledge of the size distribution of long-period comets has led to much lower estimates. The mass of the inner Oort cloud is not currently known. If analyses of comets are representative of the whole, the vast majority of the Oort cloud objects consist of various ices, such as water, methane, ethane, carbon monoxide, and hydrogen cyanide. However, the discovery of the object 1996 PW, an asteroid in an orbit more typical of a long-period comet, suggests that the cloud may contain rocky objects. Analysis of the carbon and nitrogen isotope ratios in both the Oort cloud and Jupiter family comets shows little difference between the two, despite their vastly separate regions of origin. This suggests that both originated from the original protosolar cloud, a conclusion also supported by studies of granular size in Oort cloud comets and by the recent impact study of a Jupiter family comet, Tempel 1. Origin. The Oort cloud is thought to be a remnant of the original protoplanetary disk that formed around the Sun approximately 4.6 billion years ago. The most widely accepted hypothesis is that the Oort cloud's objects initially coalesced much closer to the Sun as part of the same process that formed the planets and asteroids, but that gravitational interaction with young gas giant planets such as Jupiter ejected the objects into extremely long, elliptical or parabolic orbits. Simulations of the evolution of the Oort cloud from the beginnings of the solar system to the present suggest that the Oort cloud's mass peaked around 800 million years after formation, as the pace of acceleration and collision slowed and depletion began to overtake supply. Models by Julio Angel Fernandez suggest that the scattered disk, which is the main source for periodic comets in the solar system, might also be the primary source for Oort cloud objects. According to the models, about half of the objects scattered travel towards the Oort cloud, while a quarter are shifted inwards to Jupiter's orbit, and a quarter are ejected on hyperbolic orbits. The scattered disk might still be supplying the Oort cloud with material. A third of the scattered disk's population is likely to end up in the Oort cloud after 2.5 billion years. Computer models suggest that collisions of cometary debris during the formation period play a far greater role than was previously thought. According to these models, the number of collisions early in the solar system's history was so great that most comets were destroyed before they reached the Oort cloud. Therefore, the current cumulative mass of the Oort cloud is far less than was once suspected. The estimated mass of the cloud is only a small part of the 50 to 100 Earth masses of ejected material. Gravitational interaction with nearby stars and galactic tides modified cometary orbits to make them more circular. This explains the nearly spherical shape of the outer Oort cloud. On the other hand, the Hills cloud, which is bound more strongly by the Sun, has yet to acquire a spherical shape. Recent studies have shown that the formation of the Oort cloud is broadly compatible with the hypothesis that the solar system formed as part of an embedded cluster of 200 to 400 stars. These early stars likely played a role in the cloud's formation, since the number of close stellar passages within the cluster was much higher than today, leading to far more frequent perturbations. In June 2010, Harold F. Levison and others have suggested on the basis of enhanced computer simulations that the Sun captured comets from other stars while it was in its birth cluster. Their results imply that a substantial fraction of the Oort cloud comets, perhaps exceeding 90%, are from the protoplanetary disks of other stars. Comets. Comets are believed to have two separate points of origin in the solar system. Short-period comets, those with orbits of up to 200 years, are generally accepted to have emerged from the Kuiper belt or scattered disk, two linked flat disks of icy debris beyond Neptune's orbit at 30 AU and jointly extending out beyond 100 AU from the Sun. Long-period comets, such as Comet Hale-Bopp, whose orbits last for thousands of years, and are thought to originate in the Oort cloud. The objects within the Kuiper belt are relatively stable, and so very few comets are believed to originate there. The scattered disk, however, is dynamically active, and is far more likely to produce the place of origin for comets. Comets pass from the scattered disk into the realm of the outer planets, becoming what are known as centaurs. These centaurs are then sent farther inward to become the short-period comets. There are two main varieties of short-period comet: Jupiter family comets, those with semi-major axes of less than 5 AU, and Halley family comets. Halley family comets, named for their prototype, Halley's Comet, are unusual in that while they are short-period comets, it is believed that their ultimate origin lies in the Oort cloud, not in the scattered disk. It is believed that their ultimate origin lies in the Oort cloud, not in the scattered disk. Based on their orbits, it is believed that they were long-period comets that were captured by the gravity of the giant planets and sent into the inner solar system. This process may have also created the present orbits of a significant fraction of the Jupiter family comets, although the majority of such comets are thought to have originated in the scattered disk. Oort noted that the number of returning comets was far less than his model predicted, and this issue, known as cometary fading, has yet to be resolved. No known dynamical process can explain this undercount of observed comets. Hypotheses for this discrepancy include the destruction of comets due to tidal stresses, impact, or heating, the loss of all volatiles rendering some comets invisible, or the formation of a non-volatile crust on the surface. Dynamical studies of Oort cloud comets have shown that their occurrence in the outer planet region is several times higher than in the inner planet region. This discrepancy may be due to the gravitational attraction of Jupiter, which acts as a kind of barrier, trapping incoming comets and causing them to collide with it, just as it did with comet Shoemaker-Levy 9 in 1994. Tidal effects. Most of the comets seen close to the Sun are believed to have reached their current positions through gravitational distortion of the Oort cloud by the tidal force exerted by the Milky Way galaxy. Just as the Moon's tidal force bends and deforms the Earth's oceans, causing the tides to rise and fall, the galactic tide also bends and distorts the orbits of bodies in the outer solar system, pulling them towards the galactic center. In the charted regions of the solar system, these effects are negligible compared to the gravity of the Sun. At the outer reaches of the solar system, however, the Sun's gravity is weaker, and the gradient of the Milky Way's gravitational field plays a far more noticeable role. Because of this gradient, galactic tides can deform an otherwise spherical Oort cloud, stretching the cloud in the direction of the galactic center and compressing it along the two axes. These small galactical perturbations may be enough to dislodge members of the Oort cloud from their orbits, sending them towards the Sun. The point at which the Sun's gravity concedes its influence to the galactic tide is called the tidal truncation radius. It lies at a radius of 100,000 to 200,000 AU and marks the outer boundary of the Oort cloud. Some scholars theorize that the galactic tide may have contributed to the formation of the Oort cloud by increasing the perihelia, the closest distances to the Sun, of planetesimals with large aphelia. The effects of the galactic tide are quite complex and depend heavily on the behavior of individual objects within a planetary system. Cumulatively, however, the tide can be quite significant. Up to 90% of all comets originating from the Oort cloud may be the result of the galactic tide. Statistical models of the observed orbits of long-period comets argue that the galactic tide is the principal means by which their orbits are perturbed toward the inner solar system. Star perturbations and stellar companion hypotheses. Besides the galactic tide, the main trigger for sending comets into the inner solar system is believed to be interaction between the Sun's Oort cloud and the gravitational fields of nearby stars, or giant molecular clouds. The orbit of the Sun through the plane of the Milky Way sometimes brings it in relatively close proximity to other stellar systems. For example, during the next 10 million years, the known star with the greatest possibility of perturbing the Oort cloud is Gliese 710. This process also serves to scatter the objects out of the elliptical plane, potentially also explaining the Oort cloud's spherical distribution. In 1984, physicist Richard A. Muller postulated that the Sun has a hitherto undetected companion, either a brown dwarf or a red dwarf, in an elliptical orbit within the Oort cloud. The object, known as Nemesis, was hypothesized to pass through a portion of the Oort cloud approximately every 26 million years, bombarding the inner solar system with comets. However, to date, no evidence of Nemesis has been found, and many lines of evidence, such as crater counts, have thrown its existence into doubt. Recent scientific analysis no longer supports the idea that the extinctions on Earth happened at regular, repeating intervals. Thus, the Nemesis hypothesis is no longer needed. A somewhat similar hypothesis was advanced by astronomer John J. Matisse of the University of Louisiana at Lafayette in 2002. He contends that more comets are arriving in the inner solar system from a particular region of the Oort cloud than can be explained by the galactic tide or stellar perturbations alone, and that the most likely cause is a Jupiter mass object in a distant orbit. This hypothetical gas giant has been nicknamed Taish. One all-sky survey using parallax measurements in order to clarify local star distances, the WISE mission, is currently underway, with part of its mission being to help with either proving or disproving the Taish hypothesis. Oort cloud objects, OCOs. Apart from long-period comets, only 4 known objects have orbits which suggest they might belong to the Oort cloud. 90377 Sedna, 2000 CR, 2006 SQ, and 2008 KV. The first two, unlike the scattered disk objects, have perihelia outside the gravitational reach of Neptune, and thus their orbits cannot be explained by perturbations from the gas giant planets. If they formed in their current locations, the orbits must originally have been circular, otherwise accretion, the coalescence of smaller bodies into larger ones, would not have been possible because the large relative velocities between planetesimals would have been too disruptive. Their present-day elliptical orbits can be explained by a number of hypotheses. 1. These objects could have had their orbits and perihelion distances lifted by the passage of a nearby star when the Sun was embedded in its birth star cluster. 2. Their orbits could have been disrupted by an as yet unknown planet-sized body within the Oort cloud. 3. They could have been scattered by Neptune during a period of particularly high eccentricity, or by the gravity of a far larger primordial trans-Neptunian disk. 4. They could have been captured from around smaller passing stars. Of these, the stellar disruption and lift hypotheses appear to agree most closely with observations. Some astronomers prefer to refer to Sedna and 2000 CR as belonging to the extended scattered disk rather than to the inner Oort cloud. Modified Newtonian dynamics within the Oort cloud. It has been suggested that at their distances from the Sun, the objects comprising the Oort cloud should experience accelerations in the order of 10 to the power of -10 and s to the power of -2, and thus should be within the realms of which modified Newtonian dynamics come into effect. According to this hypothesis, which was proposed to account for the discrepancies in the galaxy rotational curve, which are more commonly attributed to dark matter, at very low accelerations, ceases to be linearly proportional to force. If correct, this would have significant implications regarding the formation and structure of the Oort cloud. However, the majority of cosmologists do not consider modified Newtonian dynamics a valid hypothesis.